I'm Stephen Patterson, and my scenario project of 2020 was a self-balancing robot. There were several reasons for this project. I've always liked robotics and Arduino, and I saw other people on YouTube attempting this project, so I wanted to try it for myself. Mobile robots like this one are my favorite type of robot to create, so this seemed like a good fit. I love to challenge myself when it comes to robotics, and there's a big challenge with this robot. It's naturally unstable, since the robot is like an inverted pendulum, meaning the center of mass is above the pivot point. There was a long process that went into making this project. After some general research at the start of the school year, I created a prototype 3D model in Tinkercad. After locating and buying the electronic components and the construction materials for this project, I hot glued a wooden body together that eventually broke, so I had to resort to metal rods and metal hex nuts to clamp the wooden tiers in place, which you'll see later in a diagram. I then started on the programming. In total, I had to write and use 450 lines of code in C language. I soon realized that the motors I had were very weak and could not move the robot around without significant human help. I then tried motors of the same micro size that had more torque, and those were not fast enough either. After testing 3 pairs of these micro motors, none of them were powerful enough or fast enough. I then tried larger motors that had the potential to move the robot around swiftly without help. I then tuned the PID values for a long time before I finally had a consistently balancing robot. The robot I built actually works quite simply. It uses its IMU sensor to read the raw tilt value of the robot. It then does some math to get a calculated tilt angle. It uses that value in the PID equation to calculate the amount of power to give to the motors. This adjusts the robot's position over time until it is level. This flowchart depicts the logic visually. So you can see that it reads the IMU, it then calculates the pitch. The PID calculates the error from vertical, and then it moves the motors. Simple. Here are some clips of the robot in action. You can see that it's always making small tweaks to the motor power. This is because the PID is always sampling the value from the IMU. It then calculates the error and writes to the motors in order to fix the error. Even when I push, tap, or even shake the top, it still manages to stay level. You can see from the side angle, it's not making giant adjustments or oscillating back and forth. It's just making tiny tweaks that keep it always upright. In case you were curious, IMU stands for Inertial Measurement Unit, which is a combination of the accelerometer, the gyroscope, and sometimes the magnetometer. This is called dynamic balance because it means the object is constantly doing work to stay balanced. This also means it's not naturally stable because there's only 2 points of contact with the ground. What once started out as a pile of wood and circuitry is now a balancing robot. The robot I built is made up of several components. On the top, you can see the IMU sensor circuit board. On the middle tier, you can see the control board with its motor driver on top. On the bottom tier, you can see the AA battery pack with the switch on it, and on the underside of the bottom tier, you can see the yellow motors with their respective wheels. There were quite a few challenges with this project that I had to overcome. I had to try 3 motor pairs until I finally found motors that had enough speed and torque. Also, tuning the PID values took a long time to get perfect. At times it felt like it wasn't working, but it eventually balanced after lots of tuning. I learned many key concepts during this project. The first one was PID control. Before doing this project, I didn't know anything about PID. Now that I've built this robot, I can apply this technology to the robotics projects I do in my free time. PID is a mathematical control method that calculates the error from a desired value. This error value can be used to correct and control a system. IMUs. I was confused about gyroscopes, accelerometers, and magnetometers until working with an IMU on this project. An IMU is a combination of all or some of the previously mentioned sensors. Until now, I didn't know such a thing existed. Now I understand each sensor's strengths and weaknesses. The physics of the inverted pendulum. This means the mass is above the pivot point. The robot's method of balancing is very similar to an inverted pendulum. This sounded crazy at the beginning of the project, but I understand this principle now after seeing several diagrams, which I'll link in the description of this video. Traits of DC motors. At first, it seemed impossible to me that a faster motor could have less force than a slower one. However, after experiencing a faster motor not being able to move the robot nearly as much as a slower one, I see that this concept is indeed true. This is a parting clip that will sum up this project. So from all those components, I have successfully built a two-wheeled balancing robot with Arduino. Thank you for watching.